Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our applied linear algebra series, and we're going to be doing some Numpy tutorials on basically vectors, matrices, everything we've been learning so far. So we're going to get into it with code. Okay. So the first thing that we have to do is, well, we want to get the package, right? We want to get Numpy. Numpy is a package that is basically a library for numerical computing. So let me just try to import. We just do import numpy. You can name it if you want. Some name it as NP. I think that's the standard. So we call this the primary library for numerical computing in Python. Okay. And what else can we say? All right, so let's try some basic stuff. Yeah, we're also going to import matplotlib because we're going to visualize some stuff here, just in case. But I don't think we do need to do that. So this is again just a library for basically for visualization purposes. Okay, and then what else are we doing here? Mm, there are a bunch of others, but we'll stick with these. Okay, so let's start with defining vectors. That's what we're gonna do first, because that's what we know linear algebra as. We're going to define vectors as a, if you're a CS major, probably have heard of array, num array, and we note that numpy does not generally distinguish. So this library doesn't distinguish between rows and columns. So we're going to be the ones to do that ourselves. These rows and column vectors. It basically does, so it simply considers a vector as a list of numbers. What coding does. Okay, so if we cell up, this is cells marked down. It has some code here. Let's try doing something. So let's define a vector. Let's call it A. Just call it U. np.array, and then our vector is gonna contain numbers 1, 2, 3. So this is defining vector A U with three components in R3, right? 1, 2, and 3. So if we run this, we're gonna get an array of 1, 2, 3. And we can define another vector. Let's do V. And this is gonna be 4, 5, 6. So there's another array, V, with three components. So this is a three-dimensional vector. So if you run it, it works. Now we can print. So I like to do this special F formatting. Some people don't. I personally do this. I just think it's really cool. And we're gonna see some nice formatting of the two vectors. Okay. And then, well, we can do what we've been doing before. So we can do basic operations. So what have we learned so far? We've learned vector addition. We've learned scalar multiplication. We've also learned, actually that's it. We derived vector subtraction from these two fundamental ideas, these two fundamental operations. Let's try. So let's do W. We're going to say this is equal to U plus V. So we're adding the U and the V together. So if we output W, it should give me 579. Just didn't format it the nice way, but same idea, 579. I can do this. There we go. 4 plus 1, 5 plus 2, 6 plus 3. Nice. And then what else can we do? We can do a scalar multiplication, right? Yeah, I'm running out of letters. I'll do A. We could do A here. We could do scalar 2 times the U vector. So this should be 2, 4, 6 for A, right? There we go. Nice and easy. Then lastly, we can also do combination of the two. Now let's do B, which is equal to 2 times U plus 3 times B. Uh-oh, 3 times B. So if we output B is going to be 14, 19, 24. So we say that vector B is a linear combination of U and V. And so if there was a span, B belongs in the span of U and V. We're just connecting ideas here. So this is an example of a vector addition. This is an example of scalar multiplication. And this is an example of okay, done. So we can do a bunch of stuff with it, right? Just to format it in a nice way. So I just did a print. Oh, W A B. And I could do something like U. Yeah, I forgot I changed the values. 2 times U. There's an A. There's a W. This is U. This is B. So if we run it now, okay, we got it. Okay, cool. Now let's try. There are some illegal operations, right? That we can counter. So say we made a mistake of, I don't know, say we made A to be a vector of 1 to 3, right? So that's 3 components, and then we say B is 4, 5, 6, 7. And if we try adding these two guys, well, that's not going to work. It's going to give us an error. Because they're not the same size, right? We can't add A and B. B has 4 components, A has 3 components. B is in R4, A is in R3, so it doesn't work. Okay. Try another one. Oh yeah, another thing that we can do with code, which I think is pretty nice, or in Python at least. So when we're manipulating or playing around with vectors and matrices, I think this is specifically in Python. I'm not sure. It is often helpful to keep an eye of shape of vectors. So this tells us the size and matrices. So that is their lengths and what else? Number of dimensions, right? So let's try that. So if I code this up, I could do something like print shape of base, or actually in this case, let's do U. This U and V. Let's try that. So U. I can do it like this actually. Just type in dot shape, and same idea here. Shape of V. They should give me the same thing. So U has 3 rows, and V has 3 rows, and by default they have 1 column, right? So we could do that. Okay, let's actually do some simple linear algebra operations in Numpy. So starting with addition and scalar multiplication of vectors. Try to do something with, let's do some linear algebra with Numpy. So we start with addition, vector addition, and scalar multiplication of vectors. And we're also going to define functions in Python. Because if we define a function in any programming language, to be honest, it's more convenient. That way we don't have to type it again and again. Okay, let's do something that adds 2 vectors. Add 2 vectors. So these take in arguments, right? Maybe one is v1, another one is v2. So what does this, oh, I did not mean to do that. I'm going to put a comment. So this function adds 2 vectors together. Right, so we're gonna raise an error first. So we say if v1, if the shape of that is not equal to v2, then we're gonna raise a value error. And we're gonna say that vectors must be the same length or dimension, right? So that's one thing we can do. Now, otherwise, we're not gonna go through that if statement. We're gonna say n is gonna be v1 dot shape. We're gonna index it to 0 because we know that that is the length of the vector. We're gonna get returned a tuple if we get the index 0, and then we can store it in the result np dot zeros n. So there's another thing NumPy can do. We can get a bunch of zeros. Here n is the length. And so what we're doing here is pre-assigning a vector of zeros to store the result. What else are we doing? We're doing a for loop for I in range of n. So we're looping from some index I to n, in this case from 1 to n. Actually, we don't know what I is. We're going to add that result. is going to be equal to v1I plus v2I, right? We return the result. If we run this, it should work. Okay, we have that function. Let's do another one. So this one is a function that adds two vectors together. Now we can also do a scalar multiplication. Scalar multiplied to a vector. So we could do, I'm gonna just do this. Scalar vector. So again, where am I at? So again, we do n is equal to the vector shape at 0. And then we get the result. NP, I don't need to do that. NP zeros n. This is where we pre-assign it. And then we do for I in range n. We get the result by multiplying the scalar by that component. Then we just return the result. Now if I run, everything works fine. Now let's actually test out our two functions. Let's see if we can see if it works. Now let's test our functions. Let's see. So here we have np dot array. So we're gonna store 1, 2, 3 here. Let's do a y, 4, 5, 6. So we have x vector and y vector, and each have 3 components, so they're in R3. And we're gonna do z, and then we're gonna put in x and y to that function add two vectors. So if we print out z, we should just add the two things. And we get an error. Why do we get an error? That's weird. It's from, wait, what? What line is it? Oh, it's 3. Oh, I forgot to add the brackets. There we go. Nice. So we get to add z. Let's try doing w. Let's do the scalar multiply by what? What do we multiply one vector by another? Let's do 3. We multiply 3 to that x vector, so we should get 3, 6, 9. Now you can pretty print it. You can print it nicely. I'll just do the f. Didn't do that in the lecture, but I'll just do it anyway. So we just do x plus y. We're gonna get z. Let me do another one. 3 times 3 times x is equal to, we do the w. And there we have it. So we added x and y, and we also multiplied a scalar by vector x. We did all of that in code. Okay, let's try this. But here's the issue though. We never do this sort of operation because for loops are very inefficient. So the way we just did, we coded this up earlier, these functions, they're actually very inefficient ways of doing it, right? Forgot to add this. Usually when we're writing code, we want to make it as organized as possible. So I would add comments just to say what the method or what the function is doing, just to make it easier for the engineers, the readers, to see what the heck is going on. Okay, let me do this. So yeah, for loops are very inefficient. So in NumPy, we actually use vectorized operations. So this one's more of timing. How fast can code write? Can code run? So let's try doing it without that. Actually, it's really just simple. We just do z equals x plus y. W equals 3 times x. NumPy allows us to do this. That's what makes it nice. Uh-oh. If I... Ooh, I have to... I want to see what it looks like. There. We got it. Same idea. We didn't have to write functions for it, but same idea. If I pretty print it again, these are what we call... Oh, I capital that. Vectorized operations provided by NumPy. So whoever did this is really good. Really easy. And it's also fast. Fast to type, fast to run. Okay. Now to double check if this is actually true, well, if we subtract them, they should give a 0. So we check if vectorized operations provide the same output as functions that we did. Check if their difference is 0. So when we print out the function, so say when we do the add two vectors function that we did, where we made for loops out of it, we're going to subtract that output to this x plus y, and we should get a 0. And then same thing for w. So we do the scalar multiply minus this, and then we see. And we actually get zeros. So we know they provide the same output. Okay. Now it is important to understand that vectorized operations are not just pre-written functions. They're actually faster than the for loops because they are optimized at a lower level using another language like C++ or Fortran. So the idea of vectorized operations, so here's the thing. In simple terms, write down text for this. Vectorized operations are faster than for loops since they are optimized at a lower level using, you can Google it, but C++ and Fortran programming languages, which are extremely hard to master. I've seen the syntax of these things, it's crazy. The thing about Python is it's English, so you can literally understand it. Okay, let's try this. How can we say if vectorized operations are faster? Well, let's create large vectors. Yeah. So these are large. So this one is only a computer. A computer can do this. I can do this. We're gonna create a random vector. We're gonna create a vector x. That's gonna contain, how many zeros is that? 1, 2, 3, 4, 5, 6. Okay, we're gonna create a million entries. Same goes with y. We're gonna create a million entries. And so the way to check it, I would just run x. We'll see yeah. So it's a bunch of random decimals. And these are a million. So this is r to the million dimension. Okay, so we have that. And what we're going to do is time. We're going to determine the time for the for loop implementation. How long is it to complete a for loop compared to vectorized? Also going to do time for We're also going to time the vectorized operations. So let's first do the for loop short code for that. We're going to import time, and we're going to say start time is equal to time dot time, which I think is a function. Then we do z1, add two vectors. So we're doing that. We're using our functions here. That's z1. Then we end that time, time. And then we're going to print the time taken by for loop implementation. It's just going to be the difference between the end time minus the start time. Can I run this, see if it works? Oh, it does work. So it took about 0.72. And this is, okay, so it took 0.38. So it's not permanent, right? Okay, let's do the same thing for vectorized operations. We just do, again, start time, time. We do z2, we add, we end the time. Okay, and then we do time taken. So if we compare these two, look at that. Okay, vectorized operations is faster than for loop implementation. It's about 0.4 seconds for for loop and 0.0025 for vectorized. This is a million components. So here we can really see that vectorized operations are faster than for loops. Okay, cool. That was something. And same thing, we can do it for matrix operations, but okay, I'm not gonna do it now. Okay, these are a couple of stuff actually. But yeah, we can do it for matrix operations. I'm just gonna copy paste the code. So again, this is for adding and matrix vector product. That's the for loop implementation. And so if we run this, now we can activate their functions. We can use their functions. And if we try this out, well, we'll see a couple of them. So here we have 1, 2, 3, 4, 5, 6. This is a 2x3 matrix, 2 rows and 3 columns. Another 2x3. We have an x vector that's in R3. If we add the two matrices, actually let's just run this whole thing. We add them, we get 8, 10, 12, 14, 16, 18. So you just add their corresponding entries. And then when we get the mat vec, well, same thing. So we just do dot products of each, but we do it in code, and we get this 1432. What else? Okay, what else? Oh, we're gonna compare it to vectorized operations and check if they're the same output. We just subtract, and we should get 0, 0. So we know that the vectorized operations is the same as the for loop implementation. Okay. Now, the performance gap between for loops and vectorized operations grows dramatically as we nest for loops. So, for example, using the double for loops in the matrix addition and matvec product functions above can lead to significantly lower performance than the built-in functions. So when doing linear algebra and writing code in Numpy, we need to do our best to avoid using for loops and rely on vectorized operations as much as we can, because it's more efficient that way. And finally, we look at how we can manipulate and access elements of arrays, vectors, and matrices in Python. So these are useful tricks that allow us to get around writing lengthy functions that need to use many for loops and take memory. Okay. So what we want to be doing is vectorized operations. Okay. Mm. Yeah, I'm not gonna talk about these other ones because these are just more extra stuff, not super needed, but yeah. Okay. So I hope you guys enjoyed this video, and I hope you learned something from coding at least. This is not an intro to coding class. I'm gonna be honest. I thought it was gonna be an intro to coding and Python. It wasn't. So I had I have minimal background in Python, so I could understand the code a bit. But yeah, this is not something I could take if I didn't know coding. But yeah, I mean coding's fun. You know, you get to do what you've been doing in math and applying it and automating it, which I think is convenient. So I hope you guys learned something from this, and I'll see you all in the next video, which is going to be the lecture.